I will begin. Dear Heavenly Father, we thank you for this day, and I thank you for these students. I just pray that you'd bring understanding to us this day, Lord. In your name I pray. Amen. So I worked through the lemma in the book. Let me get that out of the way right quick. So this is lemma 3.4.6 in your book. And it has f from u to the reals smooth, where u is convex domain in Rn containing P all right. Then there exist smooth, n smooth functions, a sub I, that go from u to the reals, satisfying a sub I of p equals to 0 for all and grammar. Fine. F of x equal to f of p, f of p. Ooh, hopefully I can talk today. I equals 1 to n, x sub I minus p sub I, partial f, partial xi at p, plus a sub I of x for all x in u. What have I done? What have I done? So this is that technical lemma that I had mentioned yesterday, listen to me, Friday, when we were trying to prove that,
When you say then there exists n smooth functions, is that like n smooth functions or n smooth?
n smooth functions, a1, a2, a3, a4, a5, n of them. Yes.
They're all smooth. They're smooth.
Smooth.
They're
Smooth
not-
means infinitely differentiable,
they're not
so
n smooth.
Yes.
I would say
It's just n
I would
of
say
them.
n differentiable. Yeah.
Oh, so they are infinitely differentiable, or they're...
Yes. Yeah, they're smooth.
Okay.
Smooth means arbitrarily many derivatives exist and are continuous.
So it shouldn't be hyphenated there?
No, n smooth. Like there are n. I don't know.
This is a problem with functions.
Whatever you guys want. All right. So that's bothering you. Okay. I'm sorry. What? Why is this? Sorry, my computer's bothering me. Okay, so proof. So what does convex mean? Convex means that, it's a domain, so it's an open connected set, right? And convex means that if we have P and if we have X, then the line segment which connects those two is inside U. So in particular, that means that you could use the notation px. What that would mean is, 1 minus t times p plus tx, 0 less than or equal to t, less than or equal to 1. That's just the parameterization of the line segment that starts at p and goes to x at time 1, And the point is all those points would be a subset of U. All right. And so here's the thing we do. We do f of x minus f of p, all right? That's equal to the integral from 0 to 1, all right, of d dt of what? Of f of p plus t times x minus p. You notice that that's also the typical point in the line segment from p to x. Yeah? Why can we do, I mean, so you're taking the total derivative of a function, right? Fundamental theorem of calculus, your net change theorem, whatever you want to call it. If I plug in t equal to 0, what do I get? F of p from the lower bound. What do I get from t equals to 1? I get x, right? So this is just fundamental theorem of calculus applied to the, I mean, this is, f is a function of many variables, but we're feeding it a path, which means that this is in total a real valued function of a real variable, right? But also, by the chain rule, that total derivative can be rewritten, right? So how does it look like? It looks like partial f partial x1 at the point, I'm tired of this. Let me call this stupid thing star. At star, okay, times what? If you differentiate this with respect to, I mean, let me just write it this way for just a second. Partial x1, partial t, right? Plus da 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 da, plus partial f, partial xn at star, partial xn, partial t. And these shouldn't be partials. These are total derivatives. Sorry, this is just the chain rule. Chain rule. And here I'm using x1 through xn for the notation of the nth inside function of the star. I mean, I'm using, it's not the greatest notation, but the point is dx1 dt would be what? This being the, I mean, I'm differentiating the first component of this with respect to time. What do I pick up? That's gone. I just pick up, that differentiates to 1. I get, yeah, x1 minus p1, right? And then the next term would be like partial f, partial x2 at star, x2 minus p2, you know? And so forth. Now, here's a sneaky step. The xn and the pn, they're just numbers, right? So you can rewrite this thing as a sum of integrals. It's the sum I equals 1 to n of x sub I minus p sub I times the integral from 0 to 1 of partial f partial xi. I'll write out the star this time. P plus t times x minus p dt. But, and then here's a really sneaky move. That is the sum I equals 1 to n of xi minus pi, big parentheses, partial f partial xi at p minus the integral from 0 to 1 of partial f partial xi at p plus t times x minus p, minus partial f partial xi at the point p dt. Which might look like a bit of dark magic to you until I explain the entirely trivial step which we just did. This is a number. We're using the identity, the integral of number, dt, from 0 to 1 equals number. And also, if you subtract the number, and if you add number here, oh, did I'm missing a, maybe off by a sign. Oh, it's easier. Still in the marker. There. Now the confusion will wash away. Okay, so yeah, so it's this which is already existing, right? Still there. And then just subtract this and add this. And then, well, what are we trying to do? We're trying to write f of x is equal to f of p plus the sum xi minus pi of stuff like this, right? So we've got our partial f partial xi of p right here, right? So this monstrosity is a sub I of x. And you can check that if you plug in p, what happens? A sub I of p is equal to 0. It remains, of course, to show that those are smooth, which I won't do. And I'm a little bit, I mean, I like this proof. It's nice and it's relatively easy to follow. I mean, I got this from McNerney. You know, it's his proof of lemma 3.46. And it's okay, but I know I've seen a different argument in like in my notes I reference Conlon, Lawrence Conlon's book. I remember in his book it was clear why it's important that you have smooth, because he used the Taylor polynomial in some kind of non-trivial way, and you can see that why you need the next derivative to exist to continue on. So this is not the best proof, but this is an entry-level proof to this result. It has hidden the deeper truth, which is that you need smoothness to get that the derivations are n-dimensional. That, to me, is not at all clear from this proof. So, but I thought it would be good to work through with you guys just to, you know, good thing to get us started on. Not especially exciting, but all right. So we got tangent space, right? What's the deal with tangent space? So tangent space to P at M, we can either look at as, you know, we have different views, right? We can look at it as equivalent classes of curves, right? We could look at it as derivations on the smooth functions defined near P, right? The germs of functions, if you want to get technical. And we could be like physicists, and we could say that they're objects that transform contravariantly. This is a very contravariantly. This is a very old school comment. This is brought to you from the absolute calculus of 100 years ago, which still exists and is very much alive in physics books. Because remember, physics is a time capsule for mathematics. It preserves mathematics, which is forgotten to us. It lives on in physics. But I explain this equivalence in my notes, and I'll let you read it. If we want to talk more about it in person, I can talk to you about it. But for the sake of not being furtherly, for the interest of not persecuting Travis further, I'm going to leave it here for this course. And we are just going to define, and we will have our cake and eat it too, but for the most part, our definition is going to be that TPM is the derivations at P. So in other words, it's X, right, at P, which is what? It's a mapping from C infinity P to where? To the reals, right? Such that what? What are the rules? XP linear, right? XP Leibniz. I think that's pretty much it. It's linear and it's Leibniz. It obeys the product rule and it's a linear transformation. These two things put together give you that it's a derivation on the set of smooth functions. So the theorem that we need the grown-up version of this lemma to really prove, and I showed you how this lemma allows us to prove it last time, is that this is the span of, you know, partial xi at P, all right? such that I equals to 1 to dot m, and x sub I, x upper. I need to start getting in the right habit. These are supposed to be upper i's, guys. I'll try to start adjusting and using correct contravariant notation. And if you don't, I won't hold it against you. I'm just going to, from this point on out, try to put indices up that should be up and indices down that should be down. I realize that I'm making a change of notation at this point, but you can forgive me. It will pay off in the end, and or I will regret it in about a half hour. We'll decide. You're here. You can tell me. Anyway, so this we might just call x. It's the bijection from this chart domain in the manifold to Rm, like that. This is, I'm assuming that this is a coordinate chart. All right, so I've been reading McNerney, and he does a lot of stuff. A lot of stuff in this book he doesn't really do for a geometric space. He does it for Rn. Right? So if you do things for Rn, the manifold, the coordinate system is just the Cartesian coordinate system. So it removes some of the abstraction, and that's good. But I will try to tell you some things about how to understand these things from an honest-to-goodness manifold perspective. I will try to write the basic theory in terms of charts. And I think it's worth it, and I'll show you. I think you'll believe me by the end of the day that it's worth it. I'm hopeful. Yeah. So this is the basis. We can build any derivation from the coordinate derivation, from these partial derivatives. To be more specific, here's the formula. Xp is equal to the sum, I equals 1 to n, of xp acting on the ith coordinate function, all right, partial xip. We can calculate the components of any derivation by acting on the coordinate functions in this way. That was the theorem we saw last time. I'll try to actually put this into practice. Yeah, go ahead.
When you write xi equals x from u to Rn, what does the equals x part signify?
Well, I'm torn. I sometimes use this for the coordinate chart.
Oh.
I sometimes use this for the coordinate chart.
Okay.
And
I think you mostly used pi last time. So
yeah, and we could also say that this is phi inverse if that's helpful.
okay, so it's just saying, so the equals x just means it's a chart.
If you read my notes, you notice that the 2011, I did almost everything in terms of phi inverse. And then in 2013, I'm like, I've had enough of this phi inverse, and I started writing everything in terms of x or chi. And I go through stages of acceptance and denial.
I think I just figured. Okay, so this was like what we were doing last time, where you were like x equals and then like x1, x2, x3, x, etc. Right here, you just wrote xi in parentheses, so signifier.
Right, right. Yeah, no, it's fine. But the x upper i's are mappings. They're real valued mappings from the manifold to the reals. Yeah. The advantage of the derivations viewpoint, there are many. One of the advantages, of course, the obvious advantage is it's algebraic, and algebra is easy, right? That's nice. It gives us something explicit and calculational that is not equivalence classes. Like equivalence classes. Nah, no thank you. The other beautiful thing about this is it is coordinate free, right? There's no coordinate system used here. If you fish into the details of the equivalence classes of curves, it's got coordinates because the alpha prime of 0 is calculated with respect to a coordinate system. So technically speaking, these equivalence classes of curves actually have paired with them a coordinate system, as is the case with these objects. These also have paired with it a coordinate system. And so to really compare anything you prove, you really need to prove coordinate independence. On the other hand, if you can make a definition in terms of derivations, it's already manifestly not depending on your coordinate system, which makes it a geometric definition, which is super nice. On the flip side, it's not so hard to calculate a derivation in terms of a choice of coordinates once you have it. And you can change coordinates. And the way you change coordinates, it's absolutely just simple. Because it's basically just this, partial xi at P would be the sum, j equals 1 to m, of partial y j, partial xi, partial y j at, well, I suppose, P, yeah. So if I had two different coordinate systems that were both present at a given point, I can change one basis to another according to the partial derivatives of the coordinate maps, one in terms of the other. I mean, I'd have to express the y sub j's in terms of the x sub i's in order to actually make this go. I have an example, an explicit example of this later. So, but anyway, and so, so if I plug this up in here to that, then I could figure out how the coordinates of a derivation transform, and we'd find out that they transform inversely. Let me not get into all that at the moment. Let's not, coordinate change, if I really do it justice, will eat 20 minutes of our time, and we'll all be confused at the end of it. It's not a good, that's a second order topic, not a first order topic. Let's stick with the first order stuff for the moment, yeah.
So why is not a coordinate chart around P?
So here, a manifold, point P, here's U, here's maybe U bar. So we have U bar Y and UX both in the atlas for M, compatible charts. And so, this, what did I just say? Can I follow my own advice for like 3 seconds? Grief. Man. I'm so easily fished in. Like, all right, I have some actual calculations then, believe it or not. So, Sam, you asked a very reasonable question, which was basically, so I defined how to take the partial derivative with respect to a manifold coordinate of a function on a manifold last time, but I had no example. So I think it's good, it's healthy, and it's also useless to see some examples of this, and you will soon see why I say it's useless. But, I mean, it's part of a larger theme. As students, we're driven to want explicit examples. May or may not be they're actually helpful. So, and that could just be poor planning on my part. I don't know. We'll see. Here's one. I have a few examples, actually. Hopefully after this you'll be bored with it. So let's look at the manifold, which is just the graph. Z equals 2 minus x squared minus y squared. And so, of course, that's one of these guys, right? So I pick my point P, and I'm going to let my real valued function f of P be kind of boring. It's going to be P1 plus P2 plus P3. All right? This is going to be the function I look at from, and the M is going to be the graph of fine. It's, what do you want from me here? X, Y, Z, such that Z is 2 minus x squared minus y squared, okay? It's the graph of that downward opening, what is that, a paraboloid, or I forget. I think it's a paraboloid, right? Okay, so first of all, and I'm going to use chi here because x is already used for something else. So chi of P, the coordinate chart, it's rather uninteresting in some sense. It's just P1, P2. I'm just going to use that. Now, what's the inverse? I'll use U and V. Well, it's going to be U comma V comma 2 minus U squared minus V squared, okay? There's the coordinate chart. There's the inverse of the chart, which we have previously called the patch, or the parameterization, the graph, right? So let me just write up the definition of how we partial differentiate with respect to the coordinates on a manifold. Here was the definition. My definition was something like this. Partial xi at p of f is equal to partial ui of f of x inverse, which would be chi inverse here, of u. And afterwards, we put u equal to x of p. So I need to calculate what is f of chi inverse of u. Now here, the u would be u comma v. All right, this u is a tuple, generally. Okay? So what is f of, this is f of u comma v comma 2 minus u squared minus v squared. All right. So by definition of my function is p1 plus p2 plus p3, right? So this is equal to u plus v plus 2 minus u squared minus v squared. All right, very exciting. All right. Now we can calculate what is partial u of f composed with chi inverse of uv. What's that give us? Well, this is, again, the point of this definition is that we're taking the function up on this abstract manifold space and we're bringing it back down to earth, right? We're making it just an ordinary function from R2 to R, which we partial differentiate like in the usual advanced calculus course. Sorry, it is fun to say that, isn't it? Tell no one, Tori. Let's see here. So 1 plus 1 minus 2u, right? And while we're at it, what would partial v of this thing be? One minus 2v, yeah. Okay, great. So what's we done next? Partial f, partial x1 at p, right? Is partial u of f composed with chi inverse, which is what I just calculated up there, of u comma v, such that u comma v is equal to chi of p. Which is 1 minus 2u, such that u equals what? U equals to P1, right? Because this is right up here. Got it? So that is 1 minus 2 P1. I would advertise, so what that really is that's 1 minus 2 times the x, oh man. See, I can't even hold to my own legalism for like 3 seconds. Upper 1, and see then these are supposed to, I'm just, fine, next example. I'll try to get it to the next example. I'll eventually, I'll get it eventually. So this is x1 of, this is of p, right? Think about the multiplication by the constant function 1, right? The x1 coordinate function. This is for arbitrary p, right? Arbitrary p, so therefore, partial f partial x1 is 1 minus 2 times x1. Likewise, partial f partial x2 is 1 minus 2x2. This is the constant function 1. 1 acting on p gives me back 1. What is f, actually? I said f of p is this. Can you tell me what that is in terms of coordinate functions? Yeah. See, that's actually p1 plus p2. What's p3? It's 2 minus p1 squared minus p2 squared, yeah? In other words, this is x1. It's x1 minus 2x1 squared plus 2 plus x2 minus, did I say 2? There's no 2 here. Minus x1 squared. Sorry, x1 minus x1 squared plus 2 plus x2 minus, I don't know why I put the 2 in the middle. There's no good reason for it. All of this acting on p, you see? So I could really express the function in terms of the coordinates on this manifold how? See, f, in truth, f is just equal to x1 minus x1 squared plus x2 minus x2 squared plus 2. This is an expression for f explicitly in terms of the coordinate functions on the manifold. And look what we just found. Someone who understood almost nothing of what we're doing here could get the right answers. That's right. Travis is like, music to my ears. But that's why this is good mathematics, is because it's good notation. It is how we do calculus on curve space. It's just systematic thievery from Rn. Shall we do another? Let's do another. This is sort of an obligatory example. Example 1, that was example 0, right? Yeah. If M is Rm, then Cartesian coordinates are in agreement. So this is really dumb. I mean, I'm not even going to, fine, I'll write it down, but it hurts me to write it. Partial xi at oi, eventually I'll put the I upstairs. F of x is going to be partial ui of f of x inverse of u at u equals to x of p. But you know what? That's actually partial ui of f of u, because the Cartesian coordinate system is the identity map, and this is just partial f partial ui, you know, at p. So there you go. Partial f partial xi at p is in fact equal to just partial the partial f partial ui at p for the stupid Cartesian coordinate systems, because the Cartesian coordinates are xi equals to ui. So yeah, most of McNerney is this. For the most part, his partial x is literally the Cartesian partial derivative that we talked about in Calculus 3, and is no different to here. All right? So example 1 is actually the dominant example in McNerney. See if I can find a better and more interesting, exciting example. Here's a marginally exciting example. How about we have this guy, and here's a patch. So this is a patch on the torus in R3. If you, yeah, I don't care for it. I'm not sure I care for this one either. But if we do phi inverse of x, y, z, it is going to be inverse tangent of y over x, comma, inverse sine of z over a. So basically, what you got to do is set this equal to x, y, z, right? And then solve for u and for v. This is that u, quote unquote. This is that v, quote unquote, from that solution. Took me a few minutes to derive this and convince myself it was okay. Of course, this has limited applicability because we're using inverse trig functions, which are, of course, perilous. So I don't want to belabor how to calculate those. It's relatively simple. What on earth did he just do? Oh. Okay. Some QR sticker code thing. I don't know. I love.
You should have just said no. No.
So.
This is serious.
I propose that the natural way to define functions on coordinates is with coordinate systems. I mean, what I say sounded nothing like nothing, didn't it? I mean, the natural way to define a function on a manifold is with a coordinate system. So how about this? F equals to the tangent of x1 plus the sine of x2. So this, by the way, is x1, x2. Hey. Oh, look. Yeah, I can't make up my mind, can I? Let's see here. Apparently, I will. This eventually will hurt us. Not. Yes. I should choose one. Anyway.
But if we do it upper, we can't say x of 1, x of 2, etc.
So, partial f, partial f, partial x1 of p is partial u of f composed with x inverse of uv, and then we put u comma v equal to x of p. So for this one, that is partial u of what? Tangent of, well, I'll in between step here. So f of curses, or was I? So this is where I'm getting into trouble. That is stink. This is my what? This is my x inverse of uv, right? So x inverse of uv is actually r plus a cosine v, cosine u, r plus a cosine v, sine u, a sine v. probably should have stopped at 2 examples. I do have 5. All right. Now, so how is f defined, right? So like f of p, what this notation means, right, is f of p is equal to the tangent of x1 of p, right, plus the sine of x2 of p. That's what this notation means. It's a sneaky notation for sums and composites and so forth. But it's rather beautiful, really, its use. So let's see here. Our p is what? X inverse. I mean, this is p, right? So literally, is that right? Sorry, brain malfunctioning. Oy. I have f of p. I see, I've got x1. Oh, I'm an idiot. That's the wrong. Yeah. I'm worked myself into a corner here somehow. Let me erase the thing that's making my head hurt. All right. x1, so what, I mean, this is, f of p is tangent of, x1 of p is tangent inverse of p2 over p1, and then plus the sine of, you see my function is rather lazy, right, p3 over a. Okay, so the point being, I have arranged it so that our life isn't too awful. p2 over p1 plus p3 over a. That's actually, this formula right here is the analog of the formula I wrote down for our first example, our 0th example, of p1 plus p2 plus p3, you know? So just, that's actually helpful for me because then I know what to do here, you know? I was getting tricked. I'm forgetting that f has this x built into it in some sense, right? I mean, that's what I was failing to appreciate. So what I'm doing is I'm partial u of f of, now what's my p1? My p1 is the thing I just erased. R plus a cosine of v, cosine of u, comma, r plus a cosine of v, sine of u, a sine of v. So I didn't really need to erase anything. I just had to come to terms with what I wrote. Yeah. So the point is, this is my P1, this is my P2, this is my P3, right? However you want to see this, I mean, you might have been able to see it a different way than me today, and that wouldn't necessarily be wrong, but so P2 over P1 is what? tangent u, right? And what's P3 over A? Oh, I'm sorry, what was I'm an idiot here. Oh, tangent inverse of P2 over P1, yeah. But maybe I should just leave that as x1 of P. It's more productive, yeah? P is arbitrary, so partial f partial x1 is secant squared of x1, yeah. So Travis, now that you understand all of these details about lifting and following map by map and so forth and so on, what do you think the derivative of f with respect to x2 is? No, what's partial f partial x2 by the same sort of calculation? What? Yeah, given that f is this. Cosine of x2. See? This definition is very easy to understand, as is evidenced by Travis finding the correct answer.
Should make a note saying that you actually are talking to a student.
No, my point is that, you know, now, the other way we could look at these things would be, I mean, this calculation may be, I mean, we could keep doing these kinds of things. And, I mean, I can state a theorem, right? You kind of see what's happening here, right? There's a pretty obvious theorem to state, and it's actually, like, stupidly easy to prove. Theorem. If we have f is equal to some function composed with, say, xi, and that's a function from the manifold, well, really, I shouldn't say the manifold, from U, which is a subset of the manifold, right, to the reals, where h is, say, a function from the reals to the reals, differentiable. Let's say smooth, let's be greedy. Smooth. Then I think you guys can tell me what's going to happen. When I calculate partial f, partial x, j, what is it going to give me? Right, how about h prime of xi times partial xi, partial xj, right? I mean, that's what we're discovering in our examples. I mean, this isn't the full calculus, let's say, but it's like a lot of what we need just to do examples. And here's the proof. So how would we do, I mean, what's partial f, partial xj at p? I'm assuming, of course, what? I'm assuming xi is the ith coordinate of a coordinate, I mean, it's the ith coordinate function of a chart on a manifold, and domains and nearness has been addressed and so forth. Okay, so this is partial uj of what? Of f of x inverse of u, right? We differentiate this thing, and then after it's done, we put u equal to x of p, right? But what is that? That is partial uj. By construction, this is h right, of x sub I of x inverse of u, putting u equal to x of p after we're done. If we have x of x inverse of u, what's it equal to? Just u, right. But notice what this is more fully is x1 of x inverse of u, comma, my 1's upstairs again. Let me bring it back downstairs for the sake of making it easier to read. x2, x of x inverse of u, xm of x inverse of u, right, is equal to u1, u2, um. I mean, let's unwrap it. That's what that notation means. So when I calculate xi of x inverse of u, it's nothing more than what? ui, right. I tell you what, I mean, there have been various points in my graduate education where I fought with this. Like, I would doubt it, you know. I would struggle coming to terms with the correctness of this calculation. I'd talk myself out of it, and into it, and waste inordinate hours thinking about this. But anyway, there it is. And so you differentiate, and this is just ordinary calculus. That's h prime of ui, right? But then the chain rule says I have to multiply by partial ui, partial uj.
Wait, am I understanding, or is like partial xi, partial xj just delta ij, or is that not necessarily the case?
It is.
Okay.
But so is this.
Right.
So what's ui when we put, that's h prime of xi of p, delta ij, which, as you pointed out, by the thing that I projected on the screen for like at least a minute, so it counts, is that. But it's for arbitrary p, consequently you have the identity, which I claimed.
Is there a reason that we don't use just delta ij in the theorem statement?
Not really. I'm just trying to emphasize the sort of
Chain rulishness.
the chain rule, yeah, the chain rulishness. Yes, perfect, thank you. There's another way to look at our example 3, which might be helpful. I think it gives you some kind of intuition for what's going on here. What's going on here? What's this whole construction about? Or about? So, you know, I have g of p1, p2, p3 equal to p2 over p1 plus p3 over a. This restricts, this is on R3. Well, a lot of it. P1 not equal to 0. Fine, you got me. So the point, though, is that G restricted to M gives me F. Right? The restriction of that G to the manifold here, I'm calling this thing M. Right? The restriction of that G to this manifold gives me the function F we differentiated. And so we could actually look at partial G, partial U in terms of partial G, partial X, partial U plus partial G, partial Y, partial U plus partial G, partial Z, partial U, you know? And what would that be? Well, that would be minus y over x squared and partial x, partial u, and plus 1 over x, partial y, partial u, plus 1 over a, partial z, partial u, getting somewhere here eventually. Oh, awful. Which is equal to, This is disgusting. 1 over x squared. I should have scanned this and projected it. I regret this. Oh, it's kind of interesting though. Where did so this you got to go back to the phi. The x of uv, y of uv, z of uv. This is x of uv. This is y of uv. This is z of uv, right? Cooper, it'd be good if you panned over there for a second. Oh, if only I had some kind of thing to make sure that people could know what I was talking about. Okay, there we go. So partial x partial u is, oh man, I need my glasses. That's sad. No, I mean maybe. I don't use it that much. I blame math homework. Let's see here. So that's y, and then that's, oh, I've got it here. Why don't I write it down? So that's minus y, which is, what is y? Minus r plus a cosine v sine u, right? What's partial x partial u? Well, that's minus r minus parentheses r plus a cosine v sine u. You got 2 sine u's here, you know, and then plus. Let me get this mess out of the way. And then the other pieces is the x, I have r. I multiplied and divided by x to get my x squared out front, right? And then the partial y partial u gives me this r plus a cosine v cosine u. So what you see what I'm doing? I changed this to an x squared over x squared. Okay, and this is just 0. As you can see, z only has a v dependence, right? So what is this? See. So we have a net total of r plus a cosine of v quantity squared divided by x squared.
There's supposed to be an a in the second r plus cosine v.
Yeah. Good catch. And what is x? X is almost the same thing, right? There's just a what? Cosine u, right? So this is really 1 over cosine squared u, which is secant squared u. Hey. Yeah. So this is how McNerney does it. Because he does everything from the chain rule applied to functions of 3 variables. It's a different way to skin the same proverbial cat. I mean, any way you slice it, we have the desired outcome, right? So, but there's another way we could look at this, which is that partial partial u is really nothing more than partial x partial u partial partial x plus partial y partial u partial partial y plus partial z partial u partial partial z. Right, this on M. So the manifold has some kind of dependence